Good things in this one for sequences. Let's prove a theorem that basically is called the Swiss theorem, and it says that if we have some three sequences that inputs are natural numbers, outputs are real numbers. If we have three sequences, so xn, yn, zn, then if xn is smaller or equal than yn is smaller than equal zn, and there exists first of all, there exists some n in naturals, such that for every n that's beyond it, and by the way, this capital case N is going to be in naturals as well, that for every n beyond this number, xn is smaller or equal than yn is smaller or equal than zn. This is not 4, this is n, these are n's. Then that implies that, and by the way, also, then we also, if we have that xn, its limit for infinity equals to some value, let's say x, but actually we wanna say it's all the same value, so let's take something more general, L. So the limit of xn as it approaches infinity is L, and that also equals to the limit of z n as n approaches infinity. Then that will imply by these two things that yn, its limit, also is this L. Alright? So that means that if we have two sequences and after some natural number input and higher than that, the two sequences that sort of will start to bound this middle sequence from both sides have the same limit value. So at infinity they go to the same conversion value, and this sequence after some natural number will be between them, definitely this will apply. Then and so by the way, we'll also write out the limits for each of these two bounding ones, the xn and zn, then yn will definitely have the same limit value. It looks obvious, but let's have a proof of this. First we should perhaps write out the sort of more routine-like limit definition that's repeated for these two. So let's say that there exists some lowercase n1 in natural numbers, such that for every n that's higher than n1, and by the way, this lowercase n's we all also mean are in naturals. I mean, we could just repeat it many times, but let's just state it here. Whenever we're considering lowercase n's, also everything's natural. Uppercase n, n1, n2, uppercase and lowercase n, all are natural numbers. So for every natural number lowercase n that beyond n1, basically the difference between xn and the limit is smaller than epsilon. And by the way, for any epsilon, anyhow small epsilon, that's a real number and positive. And also again, also for any epsilon higher than 0 that's real, there exists also some n2 in naturals, such that for every n beyond this n2, we will have the same occurrence going on for zn. So again, the same limit value. If we have minus L, this some term zn minus L smaller than epsilon for any epsilon value, meaning they are very close beyond some natural number input n. So if we have these things, actually we can rewrite as their equivalent statements to saying that this inner expression xn minus L without the absolute value is the same thing as if something is strictly smaller than epsilon in an absolute value, it means it's bigger than minus epsilon and smaller than plus epsilon. That's how you can rewrite an absolute value to get rid of it and write these inequalities, this inequality system. The same will go for Zn. So that means the same thing as if Zn is strictly between minus epsilon and epsilon. So again, the same expression, sort of. And now let's just play a little bit with the initial expression. Now we're basically almost at the end conclusion of this. If we again write out this thing, so now we're kind of getting closer to the final point of the proof. If we just write again this thing, what we can do is just subtract from each of these terms. Now they're ordered like this, right? So for some, I mean, of course, we again mean beyond some natural number n. they will be like this, alright? Xn is higher for beyond some input of natural numbers and going higher, and the term input at the same value, xn will be smaller than at the same value yn and zn, alright? As we see here. We can, if we have a comparison, just subtract or add a constant to all of them, and the ordering is still same. So let's subtract epsilon from all of them. So we can say minus epsilon, or actually not epsilon, we should subtract L. So this works, alright? Because, yeah, L from all of them, the limit value. Now, if we subtract L from all of them, what we get is we know at the same time that xn minus L is bigger than minus epsilon, strictly. So we already sort of see where this is going. And Zn minus L should be, according to what we got, oh, mistake here. Minus L, alright? This is minus L, definitely. Zn minus L was in the absolute value. If we want to write as an inequality, Z sub n minus L, strictly smaller than epsilon furthermore. So it's smaller or equal than Zn, and this thing, according to this, what we wrote here is smaller than epsilon. So again, we got the same thing. When we were defining the limit via, inputs higher than n1 or n2 respectively for xn, zn respectively, we also knew xn and zn sort of bound to yn. So we intuitively knew that it was going to sort of work out. But here we have a direct proof for it. We directly showed it by manipulating this expression, because we got the explicit limit definition for these two sequences, and that told us that if we have an absolute value inside xn minus L should be smaller than epsilon, and that could be written as such. But we could just write it out here again, and then with that trick of subtracting minus L, we could realize, oh, but xn minus L is higher than minus epsilon, and zn minus L is smaller than epsilon, but between it, with these smaller or equal signs, is stuck in the y minus L. So that implicitly means this chain effect of the inequalities as we see here, right? That means that yn minus L must be also strictly between the epsilon values, minus epsilon and epsilon. So, or implies, but we can also say that's true equivalently expressed as y minus L smaller than epsilon. And of course, all along, whenever we're mentioning epsilon, we always mean any epsilon higher than 0 in real numbers. And it works out. We got to the expression of the condition for sequence to have a limit value of L. And so here we are. We saw that if xn and zn with the context that we presented have the same limit, and y is between them as such, y will have the same limit as well.